We've covered fermions. We know what fermions are, and that means that we know most of the standard model of particle physics. What's left? What's left are the bosons. Now, bosons are force-carrying particles. Force-carrying might not be the best way to think about them. It might be better and more accurate to think about them as exchange particles, the kinds of particles that occur when two fermions are interacting with each other. Two fermions will interact, they're going to release exchange particles, or they're going to exchange these exchange particles, these bosons, and voila, by virtue of having exchanged those particles, the four forces of nature are going to be manifest. It's not just the four forces of nature, there's also the Higgs field and the Higgs boson, but that we're going to get to in the next video. So let's dive right into the deep end. Here are the fundamental forces, and we have the red boxes. Those are the forces that we're going to be paying most attention to today. We're also going to talk about that blue box, the graviton. First, let's just get a basic sense of this. On top over there is the gluon. That represents the strong force. It's the particle of the strong force. Then there's the photon. That represents the electromagnetic force. And then there's the weak force, and that's represented by the W and Z bosons right there at the bottom. And finally, the force of gravity on the far right, no political affiliation, the particle through which gravity is manifested. Let's get pretty comfortable with all four of these. So let's start at the top with the gluon. The strong nuclear force is represented by this gluon. And while we only see one gluon here, in fact, there are 8 distinct types of gluons, all of which carry the strong nuclear force. What is the strong nuclear force? The strong nuclear force is the force of nature that holds protons and neutrons together in the nucleus of an atom. But it doesn't only do that, it holds the quarks together that are inside those protons and inside those neutrons. And it holds them together so strongly that it's impossible to force them apart. Well, you could force them apart, but if you did force them apart, it would require so much more energy that 2 new quarks would be created, and voila, both of those quarks would be paired with the quarks that you just pulled apart. And that's why you never actually find quarks alone in nature, because the moment you could force one quark away from another, there are 2 new pairs of quarks. This is the strongest of the 4 forces, and that's why it has that effect of holding these quarks so tightly together and holding the protons and neutrons pretty tightly together. Second is the electromagnetic force, and that's represented by the photon over here. Now, there are endless types of photons because technically you have a photon at tons of different energy levels. And that means that there are tons and tons and tons of somewhat different photons. But the electromagnetic force is one that we're actually pretty familiar with. Unlike the strong force that exists at the level of the atomic nucleus and even smaller, the electromagnetic force is actually infinite in its range. However, it gets progressively weaker the farther away we're talking about. Leaving us out of the picture and light out of the picture, these photons are carrying the force of electromagnetism, and they're all massless. They're all speeding around at the speed of light, or really at the speed of photons, because that's what light is. And they are the particle/force that makes for both electricity and magnetism, which, as it turns out, are part of the same fundamental force, the electromagnetic force. And one of the very interesting results of this is that because the electromagnetic force is carried by photons, that means that when an electron falls in an orbital, or it jumps an orbital, or it does anything in that orbital that has to do with the electromagnetic force, it's going to be releasing photons and receiving photons. And that accounts for the activity of the electron, which means that the particle responsible for chemical reactions that we learned about in all these molecules and other compounds isn't really the electron, it's the photon. Then we see the W and Z bosons, or the Z and W bosons in this diagram, and these are all representative of one force. These are all manifestations of one force, the weak nuclear force. The W boson is really 2 particles. It's broken into the W plus and the W minus bosons. Plus and minus is indicative of their charge. One is positively charged, one is negatively charged. And then there's the Z boson, which is neutral. The weak nuclear force is so named because it's the weakest of the forces. And all of these particles are super, super heavy. So unlike the photon, which is massless, the Z boson is humongous. It weighs in at about the weight of 96 protons, or the size of a molybdenum atom, which is element 42 on the table. The W plus and W minus weigh in a little less at about 85 protons each, which is roughly the size of element 37, rubidium. This enormous size makes it slow moving, and that's a general rule that you want to keep in mind. The bigger the particle, the slower moving it is. And because it's so big, this force only works on a level far smaller than a proton. And this is the force that's fundamental to different forms of decay, such as beta decay. And lastly, for today, there's the force of gravity. We haven't found the particle for this. We're showing the graviton over here, but the graviton is a hypothetical particle. It's not known for sure, but it's widely believed that it's going to be real, that it's going to be discovered, and the real problem is we just don't have the technology to discover it yet, because the graviton is incredibly low energy. It's also proposed to be massless, like the photon, which means it also travels at the speed of light, which means that we technically could call it not the speed of light or the speed of the photon, but the speed of the graviton. And like the photon again, like the electromagnetic force, it has an infinite range of influence, but it tapers off to minuscule the farther away we're talking about. The last boson to consider that we haven't looked at today is the Higgs boson, and there's also one other thing that we haven't really addressed that really begs for addressing, which is, what are the limitations of the Standard Model? So in the next video, we're going to take a closer look at both of those things. What's the Higgs boson, and what are the limitations of the Standard Model? And until then, you be sitting on the edge of your seat with bated breath, because I will be back to tell you about the Higgs boson.